Hello, welcome to the TFA Tech Forum. This week, Javier will present on the RMM Stage 1 memory management. Javier, please take the lead.
Hi, thank you very much, Olivier. Hi, everyone. Yeah, my name is, as Olivier mentioned, Javier. Some of you may know me from the past. I've given a couple of presentations before. I've been working in ARM for the past almost 5 years, I guess. And yeah, most of this time I've been working on TF-RMM, and I've been in charge, among others, on the TF-RMM stage 1 memory management, and also to cover a few months ago on the stage 2 memory management. So yeah, in this presentation I'm going to discuss the stage 1 memory management. We can see here the agenda that I'm going to go through today. So this presentation, I guess, can be divided mostly into different blocks. One block is going to be a presentation in which I'm going to discuss the RMM memory layout and how we have divided the RMM memory and all the different memory regions on RMM. The second part of this presentation is going to dig a bit into the stage 1 translation library. I'm not going to go very deep into technical details or into implementation details. I'm just going to scratch a bit the surface and explain a bit the API and the different components. I will give a brief explanation of how the library is initialized. And then I'm going to talk a bit about the unit test that we have for the stage 1 translation library. And depending on how we do on time, I may give a very short demonstration of how the unit test work. And I will finish with explaining the future work that we have for the library, on optimizations and code enhancements that we have in mind, and then the questions and answers. Okay, so can everyone hear me properly and see the screen properly?
Yes.
Okay. Then, yeah, before starting, I want to introduce a little bit of terminology so we can all understand what is going to be discussed here. So I'm going to start describing the different physical address spaces that we have on the new V9 architecture. I guess most of you are familiar with this diagram here. Those of you who are not familiar, so as you may know, the ARM architecture has classically had two different secure state, which is the non-secure state and the secure state. In the non-secure state, we have our non-secure hypervisor, we have our non-secure or rich operating system with the classic user applications. On the secure state, we have the secure hypervisor, which can be SPM or Hafnium, and then we have the trusted operating system. And then below all that, we used to have the monitor, the TFA running there. So as you may know, usually TFA or the monitor software has access to all memory, non-secure and secure memory. And a secure application may also have access to other secure applications memory. So when the processor is executing in secure state, it can virtually access all memory. So that then we introduced the CCA architecture, in which we introduced two new states. So one of those states is the realm state, which is quite similar to secure state, with the difference that any memory that has been allocated to the realm state cannot be seen by any other state, not even by the monitor, by no one. And even when a realm has some memory allocated, no other realm inside the realm state can see that memory. In addition to the realm state, we also introduced the root state, which is the state at which the EL3 software, the monitor, executes. That would be our TFA. Yeah, we can see on this diagram how the realm state and the RMM integrates into the realm state. So the RMM provide hypervisor services into the realm state. Non-secure hypervisor, such as KVM, for instance, can invocate services to RMM using the RMI interface. That way, non-secure hypervisor can create, destroy realms, can manage the realms, schedule them to execute, manage the memory, and so on and so forth. And also on the realm state, any virtual machine that is running on the realm state can also invoke services to RMM through the so-called RSI, realm service interface. The EO3 software, the monitor software is actually the conduit between the non-secure hypervisor and the RMM image in the realm state. Right? Any questions so far?
So Javier, one slight elaboration. So the monitor can actually access the realm state as long as it's able to map that memory into its
Oh yeah.
Yeah.
Yeah, true. Yeah.
Yeah,
Thank you.
actually, I wondered even for the case where memory encryption is implemented, I wondered if EL3 is still able to access the realm content. On the other hand, EL3 might be the one to program the keys to the memory controller, right?
Yeah, as long as EL3 is able to program the right MEC values into the appropriate registers, it might be able to, but yeah, I'm not entirely 100% sure on that.
From a threat model perspective, root has access to everything.
Yeah.
Right.
Yeah, but yeah, what I meant by the memory cannot be seen by other states is that if it is encrypted, as far as I understand, the monitor cannot access or can access the memory, but cannot see what is there because it will be encrypted.
Yeah, not if you program the keys, right? It's able to access all the keys for all the world as well and be able to decrypt it. And that's not the design, but I'm saying from a threat model perspective, yeah, if you lose root, I think you lose access control to all physical address spaces.
Yes.
Okay, so we move to the next slide. So on the next slide, I'm going to discuss the granule state tracking. But before that, I want to also explain a bit about what a granule is. So for RMM, a granule is the minimum unit of memory that can be allocated or deallocated. Usually, the granule coincides with the size of a page. So I may use granule and page interchangeably here, although I'm going to try to use granule as much as I can. So yeah, and I mentioned the terms delegate and delegate. So the delegate operation consists on getting a granule of memory which belongs to the non-secure state, right? And make it changing is a secure state from non-secure into realm state. So then that memory belongs to the realm state. The undelegate operation is the contrary to this one. So we get a granule of memory which belongs to the realm state, and we change its path, its physical address space from realm to non-secure. So that memory is then available to the whole system. Usually when we create realms or when we do operations with realms, the way we allocate memory is just to get granules of memory, we delegate them, and then those are available for RMM to populate it with the realm image or with other information that the realm may need. So that's RMM needs to keep track of all the memory that can be delegated on the system. So it needs to keep track of all the non-secure memory on the system that it can be mostly all the DRAM memory. and it needs to be, and in order to do that, it needs to use a very large array of data structures called granule. So this data structure is used to keep track of the state of a granule, so we can know if this granule has been delegated or not, and if it has been delegated, whether what is the use of that granule. For instance, on the state there, for instance, we can mark a granule as being part of a translation, as being a translation table for a realm, as being a realm descriptor, as being a realm execution context, and so on. The state of a granule can be a precondition for any RMI or SMC or RMI or RSI call into RMM. So, for instance, if we make a RMI call to RMM and we pass a realm descriptor with information about the realm we want to manipulate, when we check the granule structure corresponding to that granule that we passed, the state has to be marked as a realm descriptor state. Otherwise, RMM will reject the operation. That way, we guarantee that we don't accidentally destroy or corrupt wrong granules if we pass the wrong granules. Along with the information regarding the state, the granule structure also have another two fields. One of them is a spin lock, just to protect the access to this data structure, and the other one is a ref count that we use in order to keep track of how many entities are using that granule. So usually we can only undelegate a granule when its reference count has reached 0 and is not used by any other entity or yeah. Any question? Okay. Also forgot to mention when I was talking about the RMIs that the state of a granule can be a precondition to enter an RMI, but also the only way usually to change the state of a granule is through RMIs. Is through operations from the hypervisor to RMM.
So is the reason why
Yep.
you have a ref count instead of like an owner? Because it's heading or
so the reason why we have a reference count is that, for instance, we may not have an owner for a granule. However, we may have. I think that the best way to explain this is with a very specific case that we have on the state 2 translation table, right? On the state 2 translation library that we use to generate the state 2 translation tables, we can get a granule and allocate that granule as a realm translation table, right? So we will use the granule as a translation table. So usually for each entry, for each valid entry in that table, we increment the reference count.
got it.
So when we destroy that, then we cannot destroy that translation table until it doesn't have any valid entry, and the valid entry coincides with the reference count. I think that explained through an example was better than try to give you a more generic answer.
Yeah, I think I understand. I think when you're using it for intermediate page tables, you have to maintain counts basically. Okay, thank you.
Yeah, no problem. Okay, so moving on, the next slide here. So yeah, as I said at the beginning, I'm going to give first an introduction on how the memory layout for RMM was designed. So for the stage 1 translation regime, RMM use virtual host extensions, which allow us to split the 64-bit virtual address into two different address spaces. So one of them is the high virtual address region, which extends from the maximum possible address, which is all ones, down to the size of this virtual address region. And then for the low virtual address region, that one spans from 0 all the way up to the maximum size of that virtual address. So we use the low virtual address region to create what we call static mappings, which are mappings that are performed at boot time and they never change. In that area, we store, for instance, the RMM image itself, the read-only, read-write data, the uninitialized data, and some other information. And on the high virtual address region, we store what we called the dynamic mappings, which are mappings that can be changed during the RMM life cycle. For instance, when we create or destroy a realm, we need to map a lot of granules to do operations on them. Those granules are mapped in the high virtual address region. Okay, so I'm going to move through these regions and explain them more in detail. So for the states, for the low virtual address space, as I mentioned before, it stores all the static mappings. Yeah, first of all, I just noticed that there's an error here on this illustration here. So the stacks that are marked here, they don't belong to the low region. I edited that, but I think I didn't save. But yeah, the rest is as explained here. So the low level region stores all the static and in most of the cases flat mappings. So the way it works is that the linker, the RMM export symbols from the linker. Those are imported, and then we create some data structures where we define all the regions that we want to map. In the case of this code snipped, you can see that we map the RMM code, the RMM read-only areas, and the RMM read-write areas along as well as some other areas. And then we create the mappings and we enable the memu. So what happens here is that because these mappings are static, the translation tables that we create for the low level virtual address space is shared across all the CPUs. So all the CPUs use the same translation tables. All the CPUs use the same translation context, I'll explain in a little bit. So we don't need to have different set of translation tables per CPU. At this level, we can also have some other mappings. For instance, there's a page of memory shared between EL3 firmware and between RMM, where we passed some information that cannot be passed through registers during SMCs. For instance, attestation information or the boot manifest with extra information in order to boot up. So this page is also mapped in this memory area. And we can also have some other platform dependent mappings that we need to do in this area. For instance, for FVP, we mapped the UART address into this region as well once the RMM boots up. Also, I think it's worth to mention here at this point that RMM is compiled as a PIE binary. So the GOT and other relocations are fixed up when RMM boots up. So when RMM boots up, it reads all the linker symbols. It reads all the relocation tables and fix them and commit them. So then RMM can execute as a PIE binary. Any questions so far?
Do you mark the tables as read-only by any chance? Now we have some options.
Yes. The translation tables here are mapped into read-only area. So once the MMU is enabled, the translation tables are protected. They cannot be modified.
Thanks.
Any other questions? Okay, so then moving forward, the next part of the presentation is the high virtual address space. So this is actually quite different from the low one. So for starters, the high virtual address space, it has a different set of translation tables per CPU. Each CPU has its own translation context. Each CPU manages its own set of translation tables. And what we use this space is in order to map the different in order to have dynamic mappings for different granules. So for instance, as I mentioned before, each granule has its own type. So we may have a non-secure granule, which is a granule that hasn't been delegated yet. We may have a RAM descriptor granule, which is a granule that is meant to be used to store RAM descriptor information. We may have a granule to be used as a RAM translation table, and so on and so forth. So for each different type of granule that we have, there is a type of a slot in this virtual address space. So for instance, each one of these slots can map a block of 1 granule size, right? And we can only map, for instance, we can only map RMM guarantees that, for instance, a RAM translation table granule can only be mapped to a slot reserved for a RAM translation table. We cannot map different types of granules into different types of slots. That way, RMM always knows where it can find a mapped granule, and therefore we can improve performance when we access the granules that we have mapped. Also, because we are able to statically determine how many granules we are going to need to be mapped, and what type of granules are we going to need when we perform any type of operations. We are able to statically create statically allocate all this virtual address space, and then we are able to optimize the mapping and unmapping sequence in order to map granules here. So also one of the reasons why we have a different set of tables per CPU is that way the same type of granule can be mapped in the same virtual address across all the CPUs. So each CPU can have its own, let's say, a RAM descriptor granule mapped on his own translation table. So if for some reason we need to move a realm from one virtual CPU to another one, once the granule has been mapped, the CPU won't have any trouble to access to that granule, because the virtual address to which it has to access, it will always be the same regardless of the CPU. In addition to the slot buffers granules, we also map the per CPU stacks into this memory area. So in this case, we have two different stacks. We have the general CPU stack, which is mapped below the last slot. So this CPU stack size can be configured at build time. We have a parameter with which we can indicate how many pages we want to allocate for the CPU stack. And then we have another stack, which is a one-page stack, which is allocated there and is meant to be used only when we detect a stack overflow or underflow exception. So on these cases, because we cannot access the generic stack, we use this CPU exception stack in order to be able to handle this exception. Also, there is stack guards in between the different stacks, so we can detect overflows and underflows on those stacks. Okay, so yeah, the next two slides were actually the details that I just explained. I guess I went too fast and explained everything on the first slide. But yeah, here is pretty much what I said about the specifics of the different slot buffers. You can find all the slot buffer definitions inside buffer.8. And also worth mentioning here, I forgot to mention before, that because all the CPUs use their own individual translation tables, we are able to have a number of optimizations into the slot buffer component that allow us to make very efficient mapping and unmapping operations. So even though we have to do a lot of mappings and unmappings when we create or destroy realms, for instance, those are actually quite efficient. And yeah, on the next slide, I was just meant to explain what I just explained about the stacks. Is there any questions so far?
Sorry, I missed the reason for some stack region to be mapped in the low VA space.
No, in the low VA space, you mean here?
Yeah, there is stacks at the bottom. Yeah.
Yeah, no, I was meaning to remove that. Yeah, that's actually an errata. I will fix it before we post this. Just fix that, but I think I didn't save.
Okay, fine.
Okay,
Thank
but
you.
yeah, the stacks will then be there.
Thanks.
Okay. So yeah, I guess if there's no further questions here, I can move. So that was pretty much an overview of the layout that we have for the stage 1 virtual address space on RMM. We have mostly the most important concepts here was that the whole virtual address space is divided into 2 sections, and depending on which section we may have, we may share the translation tables across all the CPUs, or we may not. So yeah, with regard to the translation library itself, so the translation library comes actually is a fork from the TFA XLAT version. TFA XLAT library, the version 2 actually. We use that as a baseline, and then we modify the code to adapt it to our needs. This library is able to support up to 52 bit addresses and up to 5 levels of translation when Fit LPA2 is enabled. So the library is stateless. It doesn't store any state. So we use something that we call context, which is an abstraction, a data structure where we store like CPU state, we store the translation tables, we store the state of those translation tables, whether they have been initialized or not, and some other metadata. We have one context per CPU and per virtual address region. This is half true, half a lie. So we may have different contexts per CPU and per virtual address region. We may initialize as many contexts as we want, actually. However, the library only allows us to commit one of those contexts to the system. So once one of those contexts has been activated, the library doesn't allow to swap and use a different context and then change the translation tables. So yeah, even though we technically can create as many contexts as we want per CPU and virtual address region, we cannot use all of them. Also, the contexts can be shared across CPUs. For instance, for the low-level region, we have a context, and that context is shared across all the CPUs because they all use the same memory mappings, and those memory mappings never change. We also use the transient we use transient translation table entries for dynamic mappings. So transient entries is something we defined is a special type of invalid entry. So when we define the memory, the virtual address space, we can define an entry as a transient. When we define an entry as a transient, it means that that entry is invalid. It doesn't have any physical address mapped into it, but we can use the translation library to map a physical address on that entry whenever we need. We can create a dynamic mapping there at any point. Then once we don't need that mapping, we can destroy that mapping, and that entry will be a transient entry again. Whereas if we have any other invalid entry, an entry that wasn't specified when we created the virtual address space, and we try to map something into that invalid entry, the library will reject that mapping and will return an error. That way, we avoid, we reduce the surface of attack by only allowing dynamic mappings into specific memory regions. Okay, so the context abstraction that I mentioned before the structure of the context can be seen here. So a context structure actually has two components. One is the XLAT context configuration, which can be seen in yellow there. And then it has the translation, the XLAT context tables, which is another data structure that contains, amongst others, the translation tables themselves, along with some metadata for them. So several contexts can share the same XLAT context configuration. For instance, in the case of on one of the earlier versions of RMM, in which we didn't have stacks Yeah, one of the versions in which we didn't have the stacks on the high region, we could have a context, a unique context configuration, and then all the context could point to that configuration. In that configuration, we store all the mappings that we have defined. We store the virtual address space, size, and some other metadata that then will be used by the context itself in order to populate and create the translation tables. Any questions so far?
So config is where you set the limits of what regions can be mapped and unmapped, right? To your previous comment about XLAT table will not allow you to map arbitrarily.
Sorry, can you repeat the question? I didn't hear very well. There was a little bit of noise.
I was asking if the config is where
Yep.
you store the valid regions to be able to map and unmap both in virtual and physical address space. Okay.
Yes. So, for instance, if we go back, here in this snippet of code, you see that I define RMM code, RMM read only, read write, right? So all these data structures here, they will be stored in the config.
The config is static, is build time, right?
Yeah, the config. Okay. Yeah, well, it can also be created dynamically at runtime, as I will show in a bit. But yeah, it has to be. So the memory mappings, the memory mapping structure, which are the ones that I showed before, and they are passed in order to create the context configuration. That has to be created before the context configuration, because the context config is going to use that as an input. But yeah, I'm going to go through the context creation process in the next two slides. Hopefully that will make it a bit clearer.
Thanks.
So yeah, the initialization of the translation library is as follows. It has basically 5 steps. these 5 steps may be done by different boot paths depending on the configuration. So the first step is the creation of the XLAT map, is the declaration of the XLAT map regions. The XLAT map regions is what I saw on this slide. So first we define the regions here, and then we populate an array of XLAT map region structures with this information. So here, as you can see, I don't know if you can see my pointer here, but the last area, as you can see, RMM shared in this snippet, you can see that the physical address that is going to be mapped into this region is 0, and the size of this region is 0. We know the virtual address, which is going to be RMM shared buffer start, and we know the attributes, right? But at build time, we don't know the physical address that we are going to map here, and we don't know the size, because those are parameters that are passed by TFA to RMM when it boots RMM. So when we create the data structure, we manually, the RMM populates these 2 fields with the parameters we received from TFA. And also in this array of XLAP map region, we may also add any per platform memory mappings that might be needed by the platform. In the case of FVP, for instance, we also add a mapping for the UART. Once we have created this XLAP map array, we call XLAT context config init. So XLAT context config init, we received this array that we have created on the first step. It will receive an empty context, and it will receive some other metadata, such as the virtual address space size and so on. And it will return, upon success, it will return a populated context config. Okay, so if the config is going to be shared across several CPUs, this only needs to be done on the cold boot path, because we only need a configuration. Then the next step is, once we have the configuration, we called XLAT context init. This step here, it will create the context itself. So this API will receive the context config that we just created. It will receive some other metadata that we may need. It will receive an empty context table structure as well, and it will receive a pointer to a memory area that can be used as to store the stage 1 translation tables. Upon completion of this operation successfully, it will return a valid context. So this, if the context is going to be shared across CPUs, as we do for the low region, this can only be executed. This only needs to be executed by the cold boot path. If we need a different context per CPU, then we need to execute this on the warm path. Finally, once we have the valid context created, we called XLAT arc setup MMU config. This actually what it does is just configures all the MMU registers with information that has been populated into the context. And once we have the MMU configured, the last step is to call XLAT enable MMU. The last step will enable the MMU and make all the translation tables effective. So these 2 steps are the ones that have always been to be executed by the warm path, and they have to be executed by every single CPU, whether or not the context is shared. Okay, and to show this a little bit more in detail, I show here some of the snippets that we use to initialize the stage 1 random translation table on RMM. So the first step, which is the creation of the declaration of the XLAT-mmap region, we can see that we create an array called regions, where we pass the RMM code and all different areas that we created on the first snippet that I showed before, right? The second step that I mentioned before was the creation of the context config structure, which is done here, step 2. So we call XLAT context config init. We pass an empty XLAT context config. We specify that this is going to be for the low region. We specify we pass other information here. Where the virtual address starts, the size of the virtual address space. You can see here that we have we also pass something called the static regions. This is actually the XLAT-mmap region array that we are passing, and its size in this case is regions and regions plus common regions. So common regions, you can see that is the same as we define on the step 1, and regions is actually the number of platform regions that we also need. That is defined by the platform implementer. So in this case, static regions is an array of mmap regions that has regions on it and any other platform regions concatenated to it. Once XLAT context config init has finished, we have a valid context config, and we can call XLAT context init. This will give us a valid context, which is the final piece of information that we need in order to enable the memory management unit. Then the fourth step is just to call XLAT arc setup MMU. This is on the warm path. So these steps here, steps 1, 2, or 3 are executed on the cold path, cold boot path for the primary CPU, because this is a shared context. But then step 4 calls setups the MMU registers. This is done per CPU. You can also see that below I called function called XLAT high virtual address setup. So pretty much this call here does all the steps 1, 2, and 3, and 4 for every single CPU to configure the high virtual address region, because each CPU has its own context, different context for the high region, and therefore this has to be set up on the warm path. And then once the MMU has been configured, the last step on the warm boot as well is to call XLAT enable MMU EL2. And after this call has been executed, the RMM will use the translations, the translation tables and the virtual address space. I don't know if there's any question here. Okay, so then that was as far as I wanted to go explaining the translation library. Just wanted to focus more on the layout of the memory and a little bit of on the initialization. So I guess the next step is the next slide that I had prepared was to talk a bit about the unit tests that we have for the translation library. So the unit tests are based on the fake host architecture for RMM, which is an architecture that allows us to run RMM in the host development machine by emulating some of the architectural features. It is based on CPPU tests, so we define different group tests. In this case, we have two different test groups, sorry, for the translation library. One exercises the translation library with fit LPA2 enabled, and the other test group, which is xlat test no LPA2, it exercises the translation library without support for LPA2. So we can have assurance that the translation library will behave and will work as expected, whether the architecture supports LPA2 or not. So I have here, see if I can. So can you see my console?
Yes.
So yeah, I prepare here.
Javier, can you increase the font size somehow?
To be honest, I don't know. I'm worried that if I try that, let me see. File. Let me see if I can increase this. Terminal size. I think I can do it here. Yeah, let me see. Okay. Yeah, that might be a little bit too much, right?
Yeah.
Let me go. That would be easier. Yeah, I think that's better.
Yeah.
Okay. So let me clean this. So yeah, basically, in order to run the unit test, we invoke the build system, and we specify the host variant as host test, the host config, the RMM config as host config. I usually enable all the log messages, and I've also enabled coverage, so we can also analyze how much coverage our unit tests have. So we build so this is building RMM for the host architecture. And the resulting binary is a CPP utest executable. So if we list the groups, I think it was LG. Yeah, we can see here the list of different test groups that we have. So we have xlat test no LPA2 and xlat test LPA2. So we can run all the xlat tests. Build, debug. I think xlat should be enough. Yeah, this has exercised all the tests of both groups with and without LPA2 support. We have executed 186 different tests, 95 tests out of 186, and we have run 2,445 checks. As you can see here, we have all the logs generated by the translation library, by the stage 1 translation library. For instance, we can see here that it was generating all these tables, all the memory mapping regions that we've used, and everything. So that way we can validate that the translation library works as expected. Then another step that we can do is run coverage analysis. That lasts a couple of seconds. Perfect. Then we should come here, refresh this page, and here we are. So for the unit test library, we can see here xlat high, tables arc, tables core. This is all the coverage we have so far. For instance, if we go to xlat tables core, we can see all the paths that have been executed. of the path that hasn't been executed. For instance, here we have one branch hasn't been exercised by the test. So yeah, that actually gives us reassurance that the translation library is working as expected. Any questions so far? Okay.
Yeah, Javier. One question, not related to unit test, but related to your previous slide regarding the transient memory.
Yep.
Memory. So, where do we need to do some initialization for that transient memory? Yeah.
No, the transient memory. Just yeah, I should have to look for that code now. I can add it. I can add a snippet into the presentation later before we publish it into the trusted firmware page. But actually, what we do for the oh, let me go back. I was going forward instead of back. So what we do to define a transient region is something similar to what we done here to define, for instance, the rest of regions. Instead of using, for instance, a map region flat, we use another macro which is called transient region, where we specify the attributes, and we specify the size, and we specify the virtual address, and that's all that we specify. What it does then is to create some sort of template for that entry, right?
So it is like you are giving some placeholders.
Exactly.
And then basically at runtime, we are just mapping it to the actual attributes.
Exactly. So if a region hasn't been marked as transient, the library is going to reject any attempt of dynamic mapping there. Whereas if a region is marked as transient, whenever we try to do a dynamic mapping, it is going to work. That way, we enforce that we can only do dynamic mappings into the slot region.
Allocated region. Yeah. Okay. Yeah. Got it.
Okay.
Thanks.
Any more questions? Okay, so then I think just to finish a bit of talk about the future work. So the future work that we have planned for the translation library is, on first place, we have a number of recursive calls on some of the APIs, especially the ones that create the translation tables. So we are working on, we have some work planned on removing all those recursive calls. There are some also code optimizations that we have in mind in order to improve efficiency, especially when we do mapping and unmapping. Some of the error codes that we have, we need to revisit them to make sure that the error codes are consistent. We've already reviewed most of them, but I think we still have to review a couple more of them. Also, because this library is a fork, started as a fork of the TFA XLAT version 2. That library used to rely on calls to panic whenever it found an unrecoverable error. So what we have to do here is to remove those panics, and instead of panicking the system, we want to be able to report an error back to the caller, and then the caller can make a decision on whether to notify to EL3, for instance, about the failure, or abort, or do anything else. Also, by having panics on the code, we cannot properly unit test them. So that's one of the reasons why some of the compilation units on the translation library have a relatively low coverage. And most of these panics are now related to the recursive functions, because there were instances in which, when the calls fail, they couldn't undo the recursion, and the only course of action was just to panic the system. So I guess once we removed all the recursive calls that we have, we are going to be able to remove also most of the panics and replace them by return error codes. And another major change that we want to do is that this library it has two different types of APIs. One is one type of APIs do operations on the context themselves, like creating context, initializing context, and so on and so forth. And then there's another set of APIs which they do operations on a specific translation table entries. For instance, the ones that we use to map and unmap dynamic regions. So far, all these APIs are like together in the same header files. So we want to break this into different header files, and we want to group them by functionality. So that's another change, another improvement that we have pending to do. That could be a little bit intrusive because it will also mean that we need to do a lot of changes on the unit tests. That can be a little bit daunting at times. But yeah, it's also on our to-do list. And yeah, I think that was pretty much all. I don't know how we're doing on time, but yeah, you have any question? Okay, then I think back to you, Olivier.
Thank you, Javier. This is right on time.
Good.
Yeah, I'm just asking again if there is any question. If not, I will stop the recording. No. So then, thank you for this presentation and for attending.
Yeah, thank you very much.